Hi everyone. My name is Jenna Syposs, and I am currently an intern at LPI, and I'm working with Julie Stopar, and we are studying impact craters in 13 Artemis sites utilizing remote sensing data sets. Next slide, please. So before I go any further into the sites, I would firstly like to acknowledge the data sets that I utilize, along with the authors. So from left to right, I use volatile stability shapefiles by Landis et al. I use M-cube and LAMP detections from Lee et al. I use LOLA DEMs 5 meter per pixel by Barker et al. And hematite integrated band depth detections from Lee et al. And I just wanted to emphasize that my work would not have been possible without the work from these scientists. So I just definitely want to acknowledge them. Next slide, please. So this is the background image is a Lola DEM hillshade of 6 of the sample Artemis sites, and so they are highlighted in yellow bold. And you might see some black dots in each crater, which are impact craters that I've been mapping out. And the blue shapefiles are M-cube detections that I was able to create as a shapefile. And the red, green, orange dots are hematite detections, which were generously provided by Shuai Li. So thank you very much, Shuai Li. And so they represent absorption features using visible near infrared spectroscopy, so VNIR spectroscopy. And so because they're different colors, they represent different integrated band depths. So later on in the presentation, you will see a dark blue detection. Next slide, please. So this is the exact same map as the last slide. However, I've included volatile shapefiles by Landis et al. So these shapefiles represent areas of volatile areas of interest that have stable bolometric temperatures according to diviner radiometric data. And they are between 60 and 90-degree latitudes at both poles. And so in this case, I just color coded each of the shapefiles. So toluene is green, water's pink, ammonium bicarbonate's beige, ammonium carbonate's orange, and sulfur is purple. And there were many more volatiles than this. However, they overlapped visually, so I just provided a few examples. And lastly, I wanted to emphasize that although the volatiles are stable here, they may or may not exist in these regions. Next slide, please. So this is a giant table of all 13 Artemis sites. And I listed out how many PSRs there are, if there's hematite detections, areas of M-cubed H2O detections, and I identified lunar prospector hydrogen values, and I got those values from QuickMap. And I listed out the stable volatiles found in each region. Now, this is a very a long list. So because I have limited time, I'm going to highlight one region, and that is Faustini Rim A. There are some hematite detections. There are a couple M-cubed H2O areas. It has an unusually high hydrogen value from Lunar Prospector. And there are a variety of stable volatiles found in this region, including sulfur, water, ammonium carbonate, ammonium bicarbonate, and a variety of other hydrocarbons. But I wanted to also emphasize that in order to pick craters of interest, that we also need to take into account terrain and illumination, which we will see 2 different examples later on. Next slide, please. So we mapped primary craters in all 13 sites. So by primary craters, we mean craters with visible rims. So secondary craters were not utilized in the study, just because we wanted to collect accurate data. And so in ArcMap 3D Analyst, we made profile measurements of each crater. We then exported that data, and then we calculated the depth to diameter of each crater from a code. And then we then took the depth to diameter and then compared it to the nearby volatile detections. Next slide, please. So this is our first candidate crater site. It's located in peak near Shackleton. And so the image to the left is a Lola DEM hillshade with red outline primary craters. And the giant red star is our crater of interest. So I definitely wanted to point out that there's a crater behind that star. And so it's located within the light blue M cube detection region, and it's also located within the sulfur stability zone. And then the image to the right is a contour map I generated in ArcMap. They represent 200-meter elevation intervals, with the dark green representing the highest contour, and then the yellow representing like lower contour elevations. And so I display this for two reasons. One is to show the correlation between lower elevations and the presence of stable volatiles, which was alluded to in the Landis et al. Paper. But my other reason for showing this contour map is to show that overall the candidate crater does have a fairly stable elevation, and so that traveling to and from the crater would in fact be reasonable. And in addition, I also found the slope value in QuickMap to be around 8 degrees, which would meet the Artemis SDT report requirements of under 10 degrees slope. Next slide, please. So this crater is 120 meters in diameter. And so the two images, the one in the middle and to the right, are profiles. One is horizontal, one is vertical. And overall, we calculated the depth to diameter ratio. And we got a value of around 0.14, which is considered very good, actually, because typical craters of this diameter have a ratio of 0.15. So it is definitely a younger crater. And so that likely means that there's less exposure of the impact materials to outside erosional factors and factors such as solar winds and radiation, which would be an interesting area of study. However, well, I think I might add that we're currently looking into the shallow crater hypothesis in the lunar South Pole. It's believed that craters in the South Pole are shallower due to the presence of ice on the crater floor. However, we sort of found that the shallowest craters tend to be found within crater walls, within like rims of craters, or within like super variable sloped areas. So overall, that's just our preliminary findings, and we'll probably have more to say about it later. But anyway, next slide, please. So our second candidate crater is within Faustini Rim A. It's located by the red star again, but you could actually see the crater in this case because it is a larger crater. So it is located within the light blue M cube detection, and there are a variety of stable volatiles in this region, including sulfur, water, ammonium bicarbonate, toluene, and even more than that. But what's most interesting about this crater is that there is a blue hematite deposit. It's the blue square, which, according to Lee et al. 2020, this definitely indicates hydration. So that is a great sign. And to the right, again, we have the contour map, which describes a little bit more variability in the terrain. So it might pose slightly more difficulties in accessing the crater compared to the peak near Shackleton crater. Next slide, please. So this crater is 2.7 kilometers in diameter. And then again, we calculate the depth to diameter ratio, and it was 0.16. But typical craters around this diameter have a ratio of around 0.21. So that suggests that this crater is slightly more eroded. But what's interesting is that it's morphologically crisp. But radar imaging has indicated that the crater is not young because the ejecta is degraded. But there's going to be more talks about Faustini Rim A tomorrow, so stay tuned for those. Next slide, please. So just to highlight both of the candidate craters, the peak near Shackleton crater is accessible. It's within the M cube section. Sulfur is stable. It is a younger, less eroded crater, which may retain its source materials better. And the crater in Faustini Rim A is within M cube detections. It contains a wide variety of volatiles that are stable. And what's especially cool is that there is a hematite a hematite detection found. And I also wanted to add at the bottom that these craters are not anonymously shallow. So one thing that could help explain the M cube detections are that there's a microscopic layer of ice on top of like the layer of on top of the regolith, or water's absorbed onto the greens, or there's bound water in the minerals, or there's somehow a hybrid of soil and water ice. So next slide, please. So I just wanted to recap that exploring both of these craters would not only help reveal the geologic history, but also like the stratigraphic history, the impact history, and the volatile abundance. So we also took into account illumination and terrain slope in the study. And lastly, I would like to say thank you to ICE50 NASA Surveys team for funding this project. So thank you very much.
All right, thanks, Jenna. We do have a couple of extra minutes for questions specifically to Jenna, and then we will move into the broader discussion period. So everyone, please feel free to put your questions in the chat. And let's see, I have a question for, oh, there's a couple of questions for Jenna, but I also have some questions. Okay, so let's see. The first question in the chat is, the hematite detections are intriguing. What is the formation process? Is the hematite expected to be disseminated throughout the regolith or concentrated in specific geological formations? Oh, okay, so that's related to my question, so I'll just bundle them together. So speaking about the presence and distribution on the surface, you mentioned that some things might just be adsorbed onto the surface, like a very thin frost. So you know, with that question in mind, is that true of all of these volatiles if they're present? And then how would that affect any sort of sampling or interaction with the surface? Like if you just disrupted the surface, would they be totally removed?
Right. So in areas where there are M cube detections, I would say it's possible to find the water frost, so to speak. But sorry, was the second question about the hematite specifically?
I guess interpret it as you will. If there's like how stable, I guess, are these volatile sources? Like if they're metastable, if you just interacted with the surface at all, would they volatilize or you know, dissociate in some way, and would you lose them, or are they stable enough that you could sample them in situ or move the surface around a bit?
Right. So the volatile shapefiles that I showed you early on in the presentation and later on also, those are areas where those elements would be stable, but it doesn't fully indicate that those volatiles are there. It's just that they're thermally stable. It's kind of like its own, I guess, PSR region for each volatile. So I would say overall, like, I don't know. I mean, there's still a lot we don't know about this region, but I'm just recounting like so far the detections and findings. So yeah.
Okay. Let's see. So then there's another question about data in general. That do you think the resolution of the data sets affects your analysis?
So we use Lola DEM's 5 meter per pixel, which is the highest resolution data set so far today. But I do question the M cube detection quality, and I would say like I do question the quality very much. I mean, all of this is like hypothetical still, but like I mean that's a very great question that I can't really answer, but sorry about that.